but thank you very much for having me. Next slide. Yes, so I'm going to be talking about antenna synthesis for Internet of Things and wireless applications. And the next slide shows my outline, and it's very short. Go to the next slide. There it is. Yeah, so, and we're just going to be talking about an introduction to antenna synthesis. I will explain our antenna synthesis system and then give some examples. Next. Antenna design is a challenging field. There's always size, cost, and performance goals. They're always increasing. There's a shortage of experienced designers, and time and budget are always under pressure. And when you're wrestling with physics, there's not as much guarantee that you're going to get the answers that you want. Productivity can be very difficult. Next. So one question is our antennas really difficult to design, or how difficult are they to design? And there's an enormous range of possible solutions for even the simplest of antennas. There's a virtually limitless number of antenna shapes to choose from. The books written on antenna design are very thick, and how do you choose which antennas to pick? And the optimum design can be very non-intuitive and difficult to locate. And if you're just doing blind trial and error, electromagnetic simulation can be very expensive in time as well as in license fees, for instance. Next slide. So just to give you kind of an example of how difficult antenna design really is, I've got a simple wire antenna. I've got two variables: the separation distance between the driven element, the dipole element, and a reflector, and also the other element, the other variable is the length of the reflector element. And I'm looking to try to maximize gain in the forward direction towards the zero, as you see on the radiation pattern. I'm looking to try to maximize that number. So the next slide shows this search space, and you can see that that peak is very narrow, and that's what we're really looking for, is that one high peak. But you can see the space is very multimodal, and if you didn't start your local search optimizer very close to the end point, that really high peak, you wouldn't find it. In addition, it is probably in a super gain mode, which is very sensitive, and you can see that the gain falls off very rapidly on one side, and so it's close to a minimum, which makes it also really, really difficult to find. Next slide. So this is a chart of how a genetic algorithm can search this kind of a space, and the synthesis tool that I've developed and that we have at AWR, National Instruments, is based heavily on the genetic algorithm. Now, a genetic algorithm, in case you are unfamiliar with that, it is an algorithm that is similar to the way one might breed racehorses. It's based on real biological genetics. Let's say you can take a design and turn it into a series of parameters: lengths, widths, materials, whatever. And let's say you take that, all those parameters, and turn them into a row of numbers, like on a spreadsheet. What you've done is created a chromosome. It's a series of instructions on how to build something. You see the screen is frozen, I'm just waiting for it. Okay. And that algorithm can be used starting with a random population, and using survival of the fittest. It can be evolved toward whatever it is you're looking to optimize for. So this is the optimization process, and it starts out with a random population searching the space, and as the generations progress, you can see it converges to those peaks that we saw in the slide that showed that graph with the different peaks, and then eventually it converges to the final peak, or at least you hope that it will converge to the proper answer. Okay, now we'll go to slide 9. Next slide. So what we're wanting to do is harness the power of this kind of algorithm and other aspects to create a system that will allow us to synthesize an antenna from just entering the specifications that we want. So we enter specifications, hit the run button, and get antenna designs out as an output. So what we need are not only the antenna optimization engine, but we also need an expert system for helping us with antenna selection, fitness scoring, how we represent the design in the optimizer, etc. And the idea is that this would be accessible for both systems and RF engineers as well as antenna experts. Go to slide 10. So how our tool works is we have antenna performance requirements that are defined by the user. It's not defined by a model per se or anything that, we don't tell the user what they need to have for their specifications. So even if it's not even physically possible, we still allow them to be entered, and the antenna system the synthesis tool will do as best as it can. It has some advanced algorithms for optimization, as kind of the example I showed before. And there's an electromagnetic solver that we use to provide an accurate evaluation of all the candidate antennas. So what we're doing is design by requirements. What you want is what you get. So you enter your requirements, you save and run, and you view the results. So next slide. So this was a project that was a good example of using this tool for a very challenging project. We were providing the antenna work for Google's Project Ara smartphone concept, and this was a modular smartphone concept, and we were trying to see how much performance we could get out of these different modules that would be plugged in and out, and we would prefer that they carried their own antennas. So we were trying to see and get real data on how much cell band performance, for instance, we could get out of these modules that we would put in and out. So what you see there, the photograph is of a Wi-Fi antenna that would be placed over a ground plane. It's only 0.5 millimeter thick, and our antenna synthesis system designed this antenna. It is given a very large number of variables that it could pick from to come up with this design, and it did very well even in this challenging environment. Go to the next slide. So the benefits for this system is that all levels of engineer can develop optimal antennas. Your less experienced designers, junior engineers, can still produce some excellent designs, and we've had some undergraduates do very, very well in their senior project designing antennas with our system. But also it can provide more insight for senior engineers. Those with a lot of experience and antenna design experience can get much more insight and quickly. Even when you've got a lot of experience, sometimes, especially when doing a new project or something that you haven't done before, it can take some time to get up to speed, and our system can provide a lot of insight very quickly and very easily. You can explore more design space with this kind of smart optimization while reducing your local EM simulation loading For instance, this tool is an online tool. It works in your browser, so you don't use your laptop or your desktop computer for it. It goes and works with a server in a back room that will do all the heavy work, and it leaves your computer free for things that you need to do. It's also scalable with compute power. As I showed with the previous example, the Google project, we had a large number of computers working on this project. And I was just one antenna engineer, but I could do entire sets of antennas for this platform overnight. So when I needed to go faster, we just got more computers, and Google's really good at having more computers. So we were able to do that very well. It also increases reliability of finding a solution quickly, because you don't have as many, so you don't have to work so hard to try lots of different antennas. The antennas are tried for you, and it reduces the amount of risk and rework that you have to do. And it's also easier to use and intuitive. One of the other advantages is that you get data very quickly, and so when you show it to your group leader or to a customer, sometimes you don't know all the specifications until a customer sees the design and sees it working and says, oh, okay, I need to change my specifications. This way you get data very quickly that you can work with. Next slide. The spec sheet is what we use to specify these different parameters that you need. The spec sheets include things like band information, your pattern and impedance information. Your geometry section gives you a bounding box so that you can constrain your geometry and input things like ground specifications. We have an antenna library that lets you pick from among different templates for different kinds of applications, or if you don't pick any, the system will select them for you. And we also have some advanced features like antenna arrays. We can co-design matching networks, work with multi-port antennas, etc. And then we have a run controls section where you determine the level of quality that you want, and you can even have the system send you an email when it's finished. Now, next slide. The spec sheet is grouped. The different spec sheets are grouped into project folders, like you would see in any CAD tool or so the various engineering tools have this tree form that's very helpful for keeping yourself organized. Next slide. And this is showing the bands and frequencies, input impedance options, and also that it can have multiple bands. So this is the top of the spec sheet here. Then the next slide, you can see the pattern requirements that you can input. And you can input areas where you maximize gain and areas where you minimize gain, and it takes you through this process. It shows you your 3D coverage map as well as a 2D slice that you can better control your specifications. You can also control your axial ratio, cross polarization, your different types of polarization can be selected all in here. Next slide. Geometry. This is the section where you would determine how large the antenna can be, and it can be it's a three-dimensional box or cylinder, and you can choose your units, and you can specify the ground separately from the main radiator, so that, say you have a device and you want to put your antenna on one corner of the device, you can specify that very readily. Next slide. Then our antenna library. This is where all the templates are for the antennas that you might choose from. And we have lots of designs and a lot of unusual designs as well. Next slide. So we're up to 189 antenna styles. And I'll show you some of those, some of the more unusual ones in the example coming up. Next slide. Okay, this is the advanced section. This is our multi-port and matching and array section. So for, say, multi-port antennas, you can specify dual polarization, for instance. Matching networks allows you to have a standard ladder network optimized along with the antenna so that you get something that you can match in your circuit. And antenna arrays, we don't do antenna arrays that are, say, 200 elements, but we can do antenna arrays that are, say, maybe 16, 4x4 or a 5x5, because they are every array is simulated with a 3D simulation, and so we can simulate subarrays, and then you can extrapolate your array performance from that if it needs to be bigger. And then next slide. Results. So when the spec sheet is run, Anson will return one or more optimized antenna designs, and we have this star rating system, kind of like you have for hotels, that will give you some idea of how well that antenna is working compared to your specifications. And you can see the what we call our dashboard over there in the corner, which will show the antenna model and its performance, pattern as well as impedance, and even coupling and excitations, etc. You can also look at the impedance, you can look at a Smith chart, and these are all user configurable so that you can go through different antennas and see if you like them. And once you find things that you like, you can download them to many different simulator and CAD formats. For instance, step files, SolidWorks, also CST, HFSS, and National Instruments' own electromagnetics tools, Analyst and Axiom. So, for instance, here's some results for a spec sheet that was run previously, and it was trying to get hemispherical coverage with circular polarization. And so here's 3 antennas that came back from a list of 68, or actually 71 different antennas came back from this one run. And you can see 3 of them here. One is kind of a standard quadrifilar helix antenna. It's got 4 feeds, and it's got a very nice pattern. You can see made the spec very, very well, but maybe that's not what you want to use, because they can also be very inefficient depending on how you feed them. So this sort of crooked wire in the middle the CWGA stands for Crooked Wire Genetic Antenna, and this is an antenna type that really has to be designed via this computer algorithm. I'm sorry, I should have told you to move forward in the slides. Yeah, so you've got these 3 different types: the quadrifilar helix that you can see, and then this crooked wire genetic antenna. And even though the wires look very random, the pattern is actually pretty decent. Not quite as perfect as the quadrifilar, but if you had a CNC wire bending machine, it might work very nicely for you. And then there's another antenna type that's completely different from the other 2, which is a Yagi antenna made of straight wire segments that has a twist in it. And it also has some pretty nice characteristics. And perhaps that could be of interest. So what you're able to do with an antenna synthesis process is get a lot of information quickly, and trade off a lot of different kinds of designs. Going to the next slide. Here's our Internet of Things example. Let's say you want a dual band Wi-Fi, and you wanted to do this in some sort of rectangular IoT device package. Compact planar geometry. I chose something like the size of a business card, 90 millimeters by 50 millimeters. An antenna would be placed along the long edge of this package. And we're looking at 2 or more ports for the antennas. And we need isolation to create decoupled channels. So next slide. So I did this 3 different ways to try to design this. First of all, I iterated the first time with just doing a single antenna, single port on dielectric, just on one corner, and then I would put more of them on this card and see how it did. And I used this mesh type antenna that you see there in the picture that allows me to do lots of different things. And I also optimized it for 50 ohms, so I wouldn't have to worry about matching. So I could use a cable feed or whatever I'd like. Go to the next page. So here's the spec sheet for this. I had 2 bands, as seen here, and I had my geometry. You can see the little window where I had my Wi-Fi antenna up in the corner of my ground plane. And I wanted also to put this over in a dielectric material, Rogers 4350B, and I had an overall efficiency of -2 dB, so it would be reasonably efficient. Next page. And so here are some results. I had a very nice VSWR of about 1.2. The patterns were, nice and blobby, nothing, reasonably efficient. And the antenna looked pretty interesting. Kind of has an open section underneath, so it has access to free space. It looks pretty reasonable. The efficiency actually was quite good on this. Next page. So I brought this into the AWR tool, Microwave Office, and simulated it again in Axiom, a 2.5D EM simulator. And now it had an infinite sheet of dielectric instead of a finite sheet, so that changed the resonant frequencies, and I needed to scale the antenna 15% smaller to hit the frequencies that I wanted to hit. But overall, the performance was very similar to what I was getting out of the synthesis tool. Next slide. Okay, so now I put in 2 of these antennas along the edge of the device, and this antenna does not work in the center of the edge. It requires a corner. So I wasn't able to get 3 antennas on one edge, but I could get 2, and they worked pretty well. The resulting coupling is actually minus 13 dB at worst between these, and the VSWR was at 2 or less across both bands. So it turned out pretty well. Next slide. Now, this approach worked for 2 antennas. I just designed one and then duplicate it and kind of hope for the best. But I would rather really design a complete design directly instead of doing it that way. And it would be nice if I had a third or another antenna type, so I could have a 3rd port in the center of the edge. So I iterated again. Next slide. Iteration 2. I did a 2-port antenna. This time no dielectric. Makes it go faster. Might help with efficiency. I can use the packaging to get a little bit more height. but I just wanted to do a direct design of a 2-port antenna before attempting a 3-port design. Again, these were 50 ohm ports, and you can see an example of kind of a random design that kind of shows what design space looked like on this slide here. Next slide. Now, I've still got my dual band, but I've got different port activations here. This is a little bit advanced. If you're working with a multi-port antenna like we have here, I've got 2 bands, or I've got 2 ports, and I need to have them each active at different times, and so that I can look at the maximum coupling between them and optimize for that. So this is one of the features we offer, and I know this is kind of a fire hose here. So that's how that works. Okay, next slide. In this case, you can see I've now got my radiator region all across the top, one edge of the device, so that I can use that for the antenna, and specified that. Next slide. So now these are the results. Has good VSWR and good coupling, quite good coupling results there between the 2 ports. And you can see that the system essentially created 2 separated antennas, almost like an array. They're not identical antennas, but they are pretty, they're somewhat similar. You can tell that there is some similarity between them. And it removed all the connections between the ports except through the ground plane. So this was the kind of answer that we were looking for. Next slide. And we went, and I put this into Axiom Microwave Office to verify my results, and yes, the coupling worked out well, and the frequency worked out well, and I didn't actually even have to modify the design at all, because there's no dielectric and no dielectric changing from Axiom to Anson. Okay, so next. So
sorry, maybe disconnect.
Yes.
Yeah. Is it? Okay, fine.
Okay. Okay. So move ahead 1 slide to 36. So we have this now this new geometry. This is just one of the antennas, and I replicate it twice. So now I've got an array of 3 antennas, each of which is somewhat smaller. And I still want them to be coupled, say minus 12 dB, and I'm going to make it a 3-element array along one edge of this business card. So next page. These are the results, and the VSWR looked pretty good, and I was able to make almost minus 12 across the dual bands. Obviously, they are much closer together, these 3 ports, so I'm not surprised that the coupling is actually somewhat a little bit higher, but it looks pretty decent. And actually, you will see that there is a connection between all 3 elements. They are actually touching each other, but they are actually pretty well isolated. If you go to the next slide, the Axiom results matched well with Anson and showed similar coupling below minus 11.5 dB, and our VSWR is still The center antenna is a little bit worse, and that's in between bands. Now, note that these antennas are actually pretty broadband. They're usable from low frequency all the way through, from the 2.4 through the 5 gigahertz, and pretty much everything in between. They're almost all with a VSWR less than 2 across that entire range. So that makes them quite usable and broadband. So next slide. To conclude, we have good results from each approach, and our results from Anson are matching well with our other simulator. Next steps, would be to look at miniaturization. How small can we make the antennas? What is the trade-off for using dielectric, and the trade-off between size and isolation? And can we add more ports? Can we add? How many ports can we actually have in this kind of a size? And what is the best antenna type to use for that? Next slide. So to summarize antenna synthesis in general, we're able to quickly create some high performance designs with multiple criteria that are competing. We have increased performance or efficiency that we can achieve using this method over standard design methods. We have a higher confidence in achieving a good result, and we can automate the discovery of design principles from which we can gain insight. And we can support a wide and growing range of specifications and applications, and it's significantly faster and lower cost than the standard design process. Less time needed to begin new designs. You can rapidly run lots of what-if scenarios, trade studies, greater agility, and all of the above leads to cost savings as well. And that is it. Thank you very much for your attention.